Okay, this is the differential equation class. We're in section 3.3. Oh, it doesn't look like a 3.3 to me. There, now it's a 3.3. So now the issue is we have things that are singular points. So if I look at an equation x, y, double prime plus y prime plus y is equal to 0. So I have something that looks like that. And I divide everything by x, and I get into a form that looks like this. Looks like that. And then I try to use my procedure for y is equal to a and x to the n guy. If I try to use that, if I try to use a series expansion, I run afoul, I won't get an answer, and the reason I do is because I'm doing an expansion around x is equal to 0, and x can't be equal to 0. Okay, and that's my problem. So this expansion, y is equal summation a n x to the n, is about x is equal to 0. So it's good plus or minus a little bit from that point, maybe up to 10, maybe up to 20, maybe up to 30. We don't do those calculations, we don't really know. But now I've got a singular point. So if I have an equation in the form axy double prime plus bxy prime plus cxy is equal to 0, I have to put that equation in the form a plus pxy plus qxy, like that. So I'm dividing by ax, and then I ask myself, is that expansion, in this case around x is equal to 0, do I have a singular point around the point that I'm doing the expansion at? And if the answer is I do have a regular singular point, I do have a singular point, singular LAR point, then I can't use summation n equals 0 to infinity a n x to the n as an expression for y. It's not going to work. And now I have to find out whether or not the singular point that I have is a regular singular point, regular singular point. From now on, we'll call it regular singular point like that, or an irregular singular point. And we'll call an irregular singular point. We'll use that abbreviation so I don't have to spell it out. Okay, now, so if I have the equation if I get in the form y double prime p of x y prime plus q of x y is equal to 0, so I can get myself into that form, and I find that either around what I'm expanding I have a singular point, then what I'm going to do is I'm going to take the limit as x goes to 0. If I'm expanding around x is equal to 0, then I'm going to go x is equal to 0. X, p of x, and I'm going to have to take the limit as x goes to 0 of x squared q of x if both of these limits exist. Then I have a regular singular point. If they don't exist, if they both don't exist, if both limits, if one of them, if either if either limit does not exist, either limit does not exist, I have an irregular singular point. And the methods of section 3, which we haven't gotten to talk about yet, won't work. So it's only going to work on regular singular points, whatever it is. Now, if I'm doing, let's say I've got something x squared minus 1 x squared y double prime plus x y prime plus y is equal to 0. Then I put that in the form y double prime plus 1 over x squared minus 1 x y prime plus 1 over x squared minus 1 x squared y is equal to 0. And where are my singular points? Well, my singular points are at x is equal to 0, because I can't divide by 0, at x is equal to 1, and at x is equal to minus 1. So those are my singular points. And now the issue is, are they regular singular points, or are they irregular singular points? So I'm going to look at x is equal to 0. I'm going to look at the limit. X goes to 0 of x times 1 over x squared minus 1 times x, and I see that that's going to be minus 1. And I look at the limit as x approaches 0 of x squared times 1 over x squared minus 1 x squared, and I find that that is minus 1. They both exist. Therefore, I have a regular singular point. I look at the point x is equal to 1. So I go the limit as x approaches 1 of x minus 1 times 1 over x minus 1 x plus 1 x squared. So that's the limit I'm looking at. These two guys go away, and I come up with 1. I look at the limit as x goes to 1, x minus 1 squared, 1 over x minus 1 x plus 1 x squared. I get that to be 0. They both exist. Therefore, I have a regular singular point. Okay, so that's how we're going to find whether or not our points are regular singular points or not, by using that method. I could have imaginary numbers. I could have had x squared plus 1 times y double prime, and when I divided it out, I would have had, and then I could have had something like this, and then my p of x could have been 1 over x squared plus 1, in which case I have singular points at plus or minus I. And I would do the same thing. I would look to see whether or not the imaginary points are regular singular points or not. Okay, now, Frobenius, F-O-R, Frobenius. We'll find, there we go, F-R-O. F-R-O-B-E-N-I-U-S. Frobenius guarantees us at least one solution, guarantees us a solution. If we have something in the form ax y double prime plus bx y prime plus cxy, if we have something in this form is equal to 0, and we have a regular singular point at the point that we're doing the expansion at, then he guarantees a solution. Now, when I had a second order differential equation, I was always looking for two solutions. This time, I may not have two solutions. I may have two solutions, that's fine, but he guarantees two. If I have an irregular singular point, I shouldn't be bothering with the method at all because it won't work. So that would be the other side of the coin. Okay, so what does he say? Well, he says what I'm going to do is I'm going to say y is going to be summation n equal to 0 to infinity of an x to the n minus r. And y prime summation n equals 0 to infinity n minus r an x to the n minus r minus 1. And y double prime is going to be in the form n is equal to 0 to infinity n minus r minus 1 an x to the n minus r minus 2. Notice that my indexing did not change. I was 0, 0, 0 the whole time. Why is that? Well, because I don't have a constant term. At n is equal to 0, this could be x to the 1/2 or x to the minus 1/2. So now that my a0 term is not going away, it's going to stay there, and as I take those derivatives. Now what I'm going to do is I'm going to do the same thing I did before, but I'm going to solve for the r first. So I'm going to do all the summation stuff, and when I get down to the last thing before I write down my recurring formula, I'm going to solve for the r. If the r is going to be if I have a second order derivative guy, then I'm going to have two r's because I'm going to have an r squared in there, and I'm going to have two of them. And then I'm going to solve for case 1, r1 is something, and solve everything, and then r2 is something and solve everything. So I'm going to have two sets of solutions. And again, Frobenius only guarantees us a solution. If we get to the point where we don't have a solution anymore, that's fine, we can just quit. That solution doesn't count. Okay? So that's the plan. Now, so before we do it, we see whether or not we have a regular singular point. If we have a regular singular point, then we can proceed. If we don't, then we can't. And okay, we're going all the way out to 33. All right. So I'm going to look at problem number 8. Problem number 1 through 8. We're supposed to find out whether x is equal to 0 is an ordinary point or not. And if it is a regular singular point, then we're supposed to find the solution. Well, maybe we better not start at number 8. Yeah, why not? All right, so I've got number 8. I got 6x squared plus 2x cubed y double prime plus 21 x y prime plus 9 x squared minus 1 y is equal to 0. So I'm going to put it in the form of y double prime plus 21 divided by 6x plus 2x squared y prime plus 9 x squared minus 1 divided by 6x squared plus 2x cubed y is equal to 0. I'm going to look at the limit as x approaches 0 of x times 21 6x plus 2x squared. Okay, and I see that that's going to be 21 over 6. And I'm going to look at the limit of x going to 0 of x squared times 9 x squared minus 1 divided by 6x squared plus 2x cubed. And I'm going to see that that's going to be minus 9 over 6. Both exist. Implying that I have a regular singular point. If it is a regular singular point, find the exponents of the differential equation at x is equal to 0. Okay, so all we're doing is finding the r's. That's all it wants us to do. Okay, so that's all we're going to do. So I've got 6x squared plus 2x cubed summation n equals 0 to infinity, n minus r minus 1, a n x to the n minus r minus 2 plus 21x summation n equals 0 to infinity, n minus r a n x to the n minus r minus 1 plus 9x squared minus 1 summation n equals 0 to infinity, a n x to the n minus r equals 0. All right, well, at that point, we don't have a whole lot of room, so I guess we'll just have to write smaller. So I've got summation n equals 0 to infinity of 6 n minus r minus 1 a n x to the n minus r plus summation n equals 0 to infinity 2 n minus r minus 1 a n x to the n minus r plus 1 plus summation 0 n equals 0 to infinity 21 n minus r a n x to the n minus r plus summation n equal 0 to infinity 9 a n x to the n minus r plus 2 minus summation n equals 0 to infinity 9 a n x to the n minus r is equal to 0. All right. Did I do that right?
I was just trying to figure out what it was. The first set of blue lines, second summation.
Okay, right here we have 2x cubed. So there's the 2. There's all that guy. And x cubed makes x to the n minus r plus 1.
Okay.
Because I have a plus 3.
Okay.
Plus 3 minus 2 makes it plus 1. All right, now we got to do some substitution. Let's see. We'll do a substitution into this guy, and we'll do n is equal to n minus 1. and then we'll do a substitution in this guy. N is equal to n minus 2. Okay, when we do that, then we're going to have everybody at n minus r. Okay, that's the plan. Okay, so I've got summation 0 to infinity 6 n minus r minus 1 an x to the n minus r plus summation n equal 2, no, n equal 1, n equal 1 to infinity 2 n minus 1 minus r n minus 2 minus r an x to the n minus r plus summation n equals 0 to infinity 21 n minus r an x to the n minus r minus summation n equal 0. We're on this one, right? Okay, so n is equal to, and it's not negative. So positive n is equal to 2 to infinity. We have a minus 1 sitting there, right? N minus 1. Yes, we do. Okay, where are we here? We're back on this guy. We have a n minus 2 x to the n minus r. And then we got a minus summation n equals 0 to infinity.
There's supposed to be a 9 in front of that?
9. Oh, maybe so. Yeah, 9. There's a 9 an. That's nice, you know, having 9s and a's. That just blows everybody's mind. An x to the n minus r is equal to 0. Alright, so now we're going to take the n equal 0 term and the n equal 1 term out of him, the n equal 1 term out of him, the n equal 0 term and 1 term out of him, the n equal 0 term and 1 term out of him, and then we can have summation n equals 2 to infinity when I get done. Alright, now I'll see if we can, okay, so when n is 0, I'm going to have 6 minus r minus 1. A 0 x to the minus r. When I take out the n equal 1 term, I'm going to have plus 6 1 minus r 1, no, just minus r a1 x to the 1 minus r. Then I'm going to take the 1 term out of here, so it'd be 2 minus r, the 1 term out of there, minus 1 minus r, a0 x to the 1 minus r. Okay, then I'm taking the 0th term out of this guy, 21 minus r, a0 x to the minus r, plus, I'm taking the 1 term out of this guy, 21 1 minus r, a1 x to the 1 minus r. Then I'm taking the 0 guy out of him, minus 9 a0 x to the minus r, and the 1 term minus 9 a1 x to the 1 minus r plus summation n equal to infinity of everybody else that I don't really care about. Because it's not asking me for the recurring formula, it's not asking for the solution, it's only asking me for what r is, because it's asking for the exponents of the series in question, which is a good thing. All right, now, that being the case, the x to the minus r terms, there's only 2 of them. There's 3 of them. There's 3 x to the minus r terms. And then there's 1, 2, 3, 4 x to the 1 minus r terms. But the x to the minus r terms have to be 0. Okay. All right. And the x to the minus r terms all have a 0 in them, right? Right. All right, so I have 6 minus r minus 1 plus 21 minus r minus 9 has to be 0. I don't have a choice. All the x to the minus r terms, their coefficients have to be 0. All right, so now I got 6r squared plus 6r minus 21r minus 9 is 0. I got 6r squared minus 15r minus 9 is 0. I have 3r squared minus 5r minus 3 is 0. Can I factor that? 3r, r. I don't see it factoring. Do you see it factoring? Oh, it's too late in the day to see it factoring, I suppose. Okay, so r is going to be 5 plus or minus the square root of 25 minus 4 times a minus 9 divided by 6. So r is going to be 5 plus or minus divided by 6, square root of 25 plus 36. 5 plus or minus 61. The square root of 61 over 6. I find that hard to believe. Do you guys, anybody out there find that hard to believe? I knew I shouldn't have started with that one. Number 8. All right, clearly I'm supposed to get minus 3.5. I don't see minus 3.5 there, do you? So clearly I made a mistake someplace. Bummer. And it's all Andy's fault because he's sitting in the front row. I know. That's the problem. The problem is we don't have a big enough piece of paper. Right there. See that minus sign? That pisses me right off. There's a minus sign right here. There's a minus sign right there. Nope, there's 2 minus signs right here. n is equal to 0, n is equal to 0, n is equal to 0. So those are the only guys that are going to be there. 6 R 21 minus R and a minus 9. R squared 6R minus 21 minus 9, 615. Well, we know that that's wrong, because there's absolutely no way that can factor the way it's supposed to factor. All right. Bring out the red ink pen. Where is the mistake? 6x, that goes away. 2x cubed, there's the plus 1. 21x, that goes away. 9x squared minus 9. Okay, we're going to do substitution n equals n minus 1, n minus 1, n minus 1, a n minus 1. A n minus 1. Substitution n minus 2, n minus 2, n minus 2. I don't see a mistake yet, do you? N is equal to 0. 6 minus R minus R minus 1. A0, blah, blah. N equals 1, we don't care. N is equal to 1. N is equal to 1, we really don't care. N is equal to 0. 21 minus R. 21 minus 1, blah, blah, blah. Okay. Minus 9 minus 9. 21 minus 9.
How come in the third term, on the black ones, you have the third term?
This
A,
guy.
You have the a to 0, and then you have x to the 1 minus r. Should that be a minus r with all the other a zeros?
No. See, that's this term right here. I just have the n equal 1. And when I go a1 minus 1, that becomes an a0. Now I need an a0 in the x to the 1 minus r term in order to find a1 later on. So once I get the right r's, I also from the x minus 1 minus r terms, I find my other variable x and my other constant of integration a1. So that's going to be set as well. So that's not a problem. The problem is I don't see how that factors 6r squared 6r minus 21r minus 9, and that's supposed to be factoring r minus a half times r minus 3. And that obviously can't factor that way. If I put a 1/2 in here, I don't get. If I put a 3 in here, 9, 27, 3 and 3. So I don't even get. I don't even get the 3 out. Oh well. Next problem. Let's try one more thing. There, now he's back on. So we found our mistake when we divided by 3. We put a 3 there when we should have had a 2r squared. And if we put a 2r squared, then this thing obviously factors into that. And my maybe it does, maybe it doesn't. Right, so I'm going to have 2r times something, r times something. And if I go minus 3 plus 1, then that's how it factors. And r becomes a minus 1/2 and a 3. So that means that the two series that I'm looking for is y would be equal to summation n equals 0 to infinity a n x to the n minus a minus 1/2. So I'm going to be if I start at 0, I'm going to start at a 1/2 and then 3/4 and then 5/8. And the other possibility is summation n equals 0 to infinity a n x to the n minus 3. So I could have a minus 3 term, a minus 2 term, a 0 term. So those are my exponents. Okay, well that solves that problem. Okay, now we're going to move down to number 10. If x is equal to 0 is a singular point, blah, 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 blah. No, we're not going to do that.
On the last problem, how
Yeah.
come you only use the ones that have an x and a minus up?
Those are the only ones I had to use. The question,
He just wants to find the r, not all the values.
yeah, I'm not finding everything. So if I use the x to the 1 minus r term, then I have an a1 and an a0 in the x is equal to 1 minus r term. Where's the other guy? Right there. And so I have an a1 and a0. I can't get rid of both of them. Okay, but I would use the x to the 1 minus r term to find a1. A0 would be arbitrary. A1 is fixed by this set of equations.
Okay, then how come you don't need the bottom part?
Well, that would be my recurring formula to solve for the rest of the a's. Yeah, so I would need it. I'm going to need it. Okay, if x is not equal to 0, a is equal to a, not equal to 0, is a regular single point second order differential equation, then do a substitution, transform it into an equation having t as the singular point. We then have an attribute, blah, blah, blah. Well, we're not going to do that. Okay, so we're going to go down to number 18. And all we're going to do is find two linearly independent Formius series solutions if they exist. All right, so I have 2x y double prime plus 3y prime minus y is equal to 0. I can put that in the form y double prime plus 3 over 2xy prime minus 1 over 2xy is equal to 0. I see that I have a singular point. If I didn't have a singular point, I wouldn't be using the Frobenius method. I'd be using the method from section 2. Okay, so I have a singular point. Is it a regular singular point? Okay, limit x goes to 0 of x 3 over 2x is equal to 3 halves. Limit as x goes to 0 of x squared minus 1 over 2x is equal to 0. Both exist. Therefore, I have a regular singular point and I can use my method. Isn't that nice? And of course on the next test you will be doing that, so that'll be pretty cool. So I got 2x summation n equals 0 to infinity n minus r n minus r minus 1 a n x to the n minus r minus 2 plus 3 summation n equals 0 to infinity n minus r a n x to the n minus r minus 1 minus summation n equals 0 to infinity a n x to the n minus r is 0. Okay, I'm going to bring things in to, so I got summation n equals 0 to infinity 2 n minus r minus 1 a n x to the n minus r minus 1 plus summation n equals 0 to infinity 3 n minus r a n x to the n minus r minus 1 minus summation n equals 0 to infinity a n x to the n minus r is 0. Okay, so I'm going to do a substitution in this one. N is equal to n plus 1. I'm going to do a substitution in this one. N is equal to n plus 1. Alright, so we got summation n equals minus 1 to infinity 2 n plus 1 minus r n minus r a n plus 1 x to the n minus r plus summation n equals minus 1 to infinity 3 n plus 1 minus r a n plus 1 x to the n minus r minus summation n equals 0 to infinity a n x to the n minus r equals 0. Okay, well, I'm going to take the n equals minus 1 term out of him, the n equals minus 1 term out of him, and then put everything in a summation sign that's n equals 0 to infinity. So that's the plan. So I've got 2 minus r minus 1 minus r a 0 x to the minus 1 minus r plus, taking it out of this guy, well, okay, 3 minus r a 0 x to the minus 1 minus r plus summation n equals 0 to infinity 2 n plus 1 minus r n minus r plus 3 n plus 1 minus r a n plus 1 minus a n x to the n minus r is equal to 0. Okay, now look at the thing outside of the the summation. They're all a zeros and they're all x to the 1 minus 1 minus r. I can divide by those things and I can have that 2 minus r minus 1 minus r plus 3 times minus r has to be 0. Okay, so I've got 2r squared plus 2r minus 3r is 0. I have 2r squared minus r is 0. I have r. 2r minus 1 is 0. So I have r's can be 0 and it can be 1/2. So I have two possibilities of solutions, one with r equals 0 and the other one r equal to 1/2. I also have a recurring formula, and my recurring formula is an plus 1 equals an divided by, here's my an, divided by all of this, 2 n plus 1 How did that happen? Two n plus 1. It's 2n plus 1 minus r. N plus 1 minus r. That's better. 2n plus 1 minus r times n minus r minus plus 3 n plus 1 minus r. Okay, so that's my recurring formula. Okay, so case 1. R is equal to 0. When r is equal to 0, my recurring formula becomes n plus 1 is equal to an divided by 2 n plus 1 times n plus 3 n plus 1. Okay. Case 2. R is equal to 1/2. Okay, so when r is equal to 1/2, my recurring formula becomes n plus 1 is equal to an divided by 2 n plus 1/2 n minus 1/2 plus 3 n plus 1/2. Okay, I'll tweak on those some. And so I got n plus 1 equals an divided by 2n squared, 2n squared, 2n, 5n, plus 3. And an plus 1 is equal to an divided by this is going to be 2n squared, 2n squared minus 1/4, 2 times 1/4. Right, that's going to be a 1/4, so that'd be a 1/2. And then it's going to be plus 3n plus 3/2. So an plus 1 is going to be an over 2n squared plus 3n plus 1. All right, so now you have two recurring formulas, one for each case, and now we're going to go and start doing something. I don't know what, but okay. So A0, now look back at the summation sign. This goes n equals 0 to infinity, right? No, it doesn't. Yes, it does. N equals 0 to infinity. So this is good for n equals 0 to infinity. So A1 is going to be arbitrary. Is A, but I have a formula for A2. Yes, I do. Okay, so A2, A1, A0 is arbitrary. A1, n is 0, is going to be A0 divided by 3. A2 is going to be A0 divided by 3 divided by 1, 1. 5 and 5 is 10. A0 over 30. A3, A0 over 30, and is now 2. 4, 8, 18, 21, divided by 21. A0 divided by 630, 630. All right, now we're going to look at the other side. And we're going to say A0 is arbitrary. A1 is going to be, that's going to be 0, A0, because that is 0. A2 is going to be A0 divided by 1 and 1 by 6. A3, A0 divided by 6 divided by, n is 2, 8, 9, 15. A0 divided by, is that 90? 90. Right, that, is that enough to check it? Yeah, that might be enough to check it. Okay, so now we're going to check if y is, for case 1, r is equal to 0. So y is going to be A0 plus A0 over 3 x plus A0 over 30 x squared plus A0 over 630 x cubed. Okay, y prime a0 over 30 plus a0 over 15x plus a0 over 210x squared. Y double prime. a0 over 15 plus a0 over 105x. Okay, now I've got 2x of this guy, and I've got 3 of this guy. I got minus 1 of that guy, and when I get done, I better have 0. And I don't. So that just pisses me off. Does that piss you right off? Alright, so what problem is this? This is problem number 18. Yeah. Alright, where did we make our mistake? Oh, when we started the problem. Yeah, oh yeah, definitely. Well, 0 and 1/2 are correct. So 0 and 1/2 is correct. So now it's a matter of, do we have the recurring formula correct? This is going to go on the other side. It's going to be an. Okay, that's fine. I've got 2 those guys. I got 3 this guys. An plus 1. And when I write down the recurring formula, an, 2 this guy, 3 of that guy. And when I say r is equal to 0, 2 times that, n plus 3 times that. Okay, I got r squared, 2n, 3n, 3. Okay, this factors a n 2n plus 3 n plus 1. Not that that matters any. A0 is arbitrary. A1 okay, this is going to be A0 over I got a 5 in there already. How could I have a 5 in the A2 term already, I wonder? A2, this is a 1. 1, 1. 1, 1. That's a 10. I get a 10 on the bottom, sure do. Okay. If this were not 30, like it's not supposed to be, it's only supposed to be a 3. You notice that? Take the derivative of that, I only get a 3. And then I look at it again, I get plus 1 minus 1. That term goes away. Okay, now I do it again, I look at the x term, and I've got minus 1/3, and I've got plus 3/15. 5/15, plus 5/15. So that term goes away. And then I look at the x squared term, and I got minus 1/30. I've got minus 1/30 plus 3 1/20 plus 2 105s. Shit. Hmm? 3 2/10s. 3 2/10s, that's what I have. 3 2/10s and 2 105s. Darn, I got a syntax error. We need to know it. Clear the whole damn thing. All right, do it one more time. Minus 1/30 plus 3 1/20 plus 2 105s equals 0. So that term goes away too. It would appear that I have the first one nailed. Okay, so the first one works. Now the second guy is going to be different. So I'm going to have a y is equal to r is equal to 1/2, right? So it's going to be a0 x to the 1/2 to the minus 1/2 plus plus what? A0 again, a0 x to the 1/2 plus a0 over 6 x to the 3/2 plus a0 over 90 x to the 5/2. Okay, is that what I really have? R is equal to minus 1/2, and I'm doing minus r. So that's what I really have. Okay, so y prime is going to be minus 1/2 a0 x to the minus 3/2 plus 1/2 a0 x to the minus 1/2 plus 1/4 a0 x to the 1/2 plus, see, 5 goes into 90 how many times? 15? 18 times? Alright, so that'd be 18 times 2, a0 divided by 36, no, 18 times 2, 36, right? 36 x to the 3/2, y double prime going to be 3 over 4 a0 x to the minus 5 over 2 minus 1/4 a0 x to the minus 3/2 plus 1/8 a0 x to the minus 1/2 plus 3 goes into there 12 times 2 is 24. a0 over 24 x to the 1/2. Okay, now I want 2x of him. I want 3 of him. I want minus 1 of him. Okay, so I'm looking at the x to the minus 2/3, 3/2, x to the minus 3/2. I have 3/2 plus 3/2, so that term goes away. I'm looking at x to the minus 1/2. Okay, I've got minus 1 of him, and then I got plus 3/2 of him, and then I've got a minus 2/4 which is also known as a minus 1/2, which is 0. So the x to the 1/2 minus 1/2 term goes away. Now I'm looking at the x to the 1/2 term, and I get minus 1. I get plus 3/4, and I get plus 1/4. And I don't have to do that. I know that that's 0. So that's 0. That term goes away. I look at the x to the 3/2 term. So I get minus 1/6. I get 3/36, which is 1/12, plus 1/12. And then I get another 1/12, plus another 1/12, which is 0. I don't have to do that in my calculator either. So that guy is 0 as well. And now I got a solution that's checking, and I'm good to go. Okay, was that fun, or was that fun? It was fun, wasn't it? Yeah. Okay, so we'll do number 20 next. We'll do number 20 last, because as long as these problems go, that's about as long as we're going to get, right? So I got 3x y double prime, 2y prime, 2y. I have to check singular points. I'm going to look at the limit. X goes to 0 of 2 of x, 2 over 3x. That's going to be 2 over 3. And I'm going to look at the limit. X goes to 0. X squared of 2 over 3x. That's equal to 0. Both exist. Therefore, the method works. Okay, so I've got number 20. I've got 3x summation n equals 0 to infinity, n minus r, n minus r minus 1, x to the n minus r minus 2, plus summation n equals 0 to infinity, 2, n minus r, n minus, we forgot the an, x to the n minus r minus 1, plus summation n equals 0 to infinity, 2an x to the n minus r is 0. Okay. We bring in that term, summation n equals 0 to infinity, 3, n minus r, n minus r minus 1, an x to the n minus r minus 1, plus summation n equals 0 to infinity, 2, n minus r, an x to the n minus r minus 1, plus summation n equals 0 to infinity, 2an x to the n minus r equals 0. Okay, I want to do a substitution. In the first guy, I'm going to have n is equal to n plus 1. Okay. When I get done, I'm going to have summation n equals minus 1 to infinity, 3, n plus 1 minus r, n minus r, an plus 1, x to the n minus r, plus summation n equals 0 to infinity, plus summation n equals 0 to infinity, 2 n minus r, an x to the n minus r minus 1, 2 a, what am I doing?
Can you just sub into the second one?
I'm going to have to do a substitution in the second one too. N is equal to n plus 1. Wake up. Somebody wake up. Anybody wake up. How's that? Is that better? Okay, so we're going to do a substitution in the second one. N minus 1 to infinity. 2. N plus 1 minus r. Minus r. A n plus 1 x to the n minus r plus summation n equals 0 to infinity 2a n x to the n minus r equals 0. Okay, now I'm going to take the n minus 1 term out of there, n minus 1 term out of here. Okay, so I'm going to n minus 1, that's going to be 3 times minus r times minus 1 minus r a 0 x to the minus 1 minus r plus, I'm going to take the minus 1 term out of this one, 2 minus r a to the 0 x to the minus 1 minus r plus summation n equals 0 to infinity. Okay, double set of brackets. 3 n plus 1 minus r n minus r plus 2 n plus 1 minus r a n plus 1 plus 2 a n x to the n minus r equals 0. Well, that was convenient. Okay, that being the case, I can divide by a0, I can divide by x to the minus 1 minus r and come with 3r squared plus 3r minus 2r is 0, implying that r is going to equal 0 and minus a third minus 1/3 minus 1/3. Okay, now that's dangerous to do. This is r plus r. So that's 3r squared. So that r times 3r plus 1. Yep, 0 and minus a third. All right. And I have a recurring formula. Minus 2an divided by 3 n plus 1 minus r n minus r plus 2 n plus 1 minus r. Okay, case 1. That's sort of like a welfare case, in case you were wondering what case 1 means. Case 1, r is equal to 0. In that case, I have a recurring formula. And this recurring formula is for all n greater than or equal to 0, because our summation starts at 0. So I have a recurring, when r is equal to 0, minus 2an divided by r is equal to 0, 3 n plus 1 times n plus 2 n plus 1. Okay. Case 2. Normally I wouldn't do case 1 and case 2 right next to each other like this, but I have to see what the recurring formula is in order to put the minus 1/3 in it. Okay, so recurring formula, minus 2an divided by 3 n plus 4/3, n plus 1/3, plus 2n plus 4/3. Okay. It'd be nice if those guys were a little bit different. Minus 2a0 divided by, I got 3n squared. I got 3n, I have 5n plus 2. Okay, and on this side I've got minus 2an divided by, I've got 3n squared. I've got 5/3 n times 3 is 5n, 6, 7. I got plus 7n. I got 4/3 plus 8/3, which are going to be 12/3, which is going to be 4. And at this point, I would rather not have done all that in my head. I would have rather to use more paper. Okay, now, my recurring formula is for an plus 1. an plus 1. Okay, so a0 is arbitrary. a1 is minus 2a0 divided by 2, minus a0. On the other side, well, forget the other side. a2 is minus 2 times minus a0 divided by 10. a0 divided by 5. a3 minus 2 a0 divided by 5 divided by, okay, now we had, n is now 2 squared is 4, 12, 22, 24. 24 minus a0 divided by 5 times 12, 60? 60. Okay, well, if it checks that far, we'll be so happy it'll be pathetic. Okay, on the other side, a0 is arbitrary. a1 is minus 2a0 divided by 4 minus 1/2 a0. a2 is minus 2 times minus 1/4, 1/2 a0 divided by 14 divided by 14. Okay, so that would just be a0 divided by 14. a3 minus 2 a0 divided by 14. Okay, so 2 goes here, 4, 12, 12, 16, 16 plus 14 is 28. 30? 30. Okay, we'll go with 30. Minus a0 divided by 7 times that is 210. Okay, so case 1, r is equal to 0. Y is going to be a0 plus minus. minus a0x plus a0 over 5 x squared minus a0 over 60 x cubed. Y prime is going to be minus a0 plus 2 over 5 a0x minus a0 over 20 x squared. Y double prime is going to be 2 over 5 a0 minus a0 divided by 10 x. Now, that's not much to work with, but if it doesn't work, it'll not work. What problem is this? This is 20. Okay, so I want 3x, I want 2, and I want 2. I don't think that works. That's 6 over 5, so that doesn't work. Okay, so look in the back of the book real quick. This is 22. Is it 22? No, it's 20. 20. So 1/3 is supposed to work, and 0 is supposed to work. They're both supposed to work.
The X term does work out.
The X term does work out?
Yeah, you have 2 and then you have 4/5 and 6/5.
Yeah, but the unit term doesn't work out. That's what.
Yeah, it does.
It does?
A -2.
Oh, right. Oh, yeah, of course it does. Oh, what are we talking about? Boom. They go away. Because this is okay, so I've got minus 2. I got 4/5. I got 6/5, which is 10/5. That term goes away. I've got 2/5. I've got 1/10. I have 3 minus 3/10. 4/10 is 2/5. That term goes away. Okay, good. So this guy's good. Okay, now we're going to look at case 2, see if he checks. Case 2. R is equal to 1. Is it 1/3? R is equal to minus 1/3. Okay, so I'm going to have y is equal to a0 x to the 1/3 minus 1/2 a0 x to the 4/3 plus a0 divided by 14 x to the 7/3 minus a0 divided by 210 x to the 10/3. Okay, y prime 1/3 a0 x to the minus 2/3 minus 2/3. Really? Yeah, I guess so. Minus 2/3 a0 x to the 1/3 plus a0 divided by 6 x to the 4/3 minus a0 divided by 63 x to the 7/3, okay, y double prime, minus 2/9 a0 x to the minus 5/3 minus 2/9 a0 x to the minus 2/3 plus 4/18 a0 x to the 1/3 minus, does 7 go into 63? It does, 9 times, right? Minus a0 divided by 27 x to the 4/3. Okay, I want 3x of that guy. I got this problem is never solved until we check it. So until you get done checking it, it doesn't work. You don't know if you have the right answer or not. 0. Okay, so I've got 2/3 minus 2/3 x to the minus 2/3. Those guys go away. I've got 1 minus 1. I've got, right here, I got 2 minus 4/3 minus 2/3. 4/3 and 2/3 is 6/3, which is minus 2. That term goes away. I've got minus 1. I've got plus 1/3. I've got 2/3. That term goes away. I've got, I don't know what I have. I have 1/7. They go away? I'll take your word for it. Boom, boom, boom. 0, check. Okay, excellent. So on the Chapter 3 test, some of the problems, there's a hint there that it tells you to check to make sure something is like something else. If that doesn't work, that means the problem's wrong. Okay, so keep that in mind. So, but that's how you do the Frobenius method. One step at a time on really big paper. Maybe we'll do some more tomorrow or next week. Maybe we won't. I don't know. I think we do, because I think 3, 4 we still do. Yeah, Frobenius method exceptional case for 3. Yeah, I'll give you an exceptional case.